of Department of Physics, Bethune College. I welcome you all to the one-day seminar on From Havens to Alternate Energy on Earth, Relating Nucleus beneath the Supreme. This is sponsored by DBT Star College, and in this time we were searching for one seminar on alternate energy. Luckily, from Professor Sanjeev Kubre, he is just like a friend and one guide of our department, I can say. And he suggested that Professor Umesh Garg, luckily he is in India now, and we are so honored to have him with us. So he has agreed to deliver a lecture. We are so much proud. So I will now request our student, Shahana Chandra. Please with our esteemed speaker, Professor Umesh Garg. He is a professor from University of Notre Dame, USA. Sir, please.
Thank you. Thank you so much.
Now I will request our student, Nitha Matharia. Please felicitate Professor Sanjeev Kubre, sir. He is scientist from Kolkata Centre.
Thank you. Thank you.
Now I will request our student Audrija to felicitate Dr. Rajashri Rao from UGC-DAE-CSR-Kolkata Centre. Students, please. Audrija and Snitha. Now our student Monushka Pitson, she will felicitate our officer in charge madam, Dr. Punshila Hajra Bhattacharya. Thank you, ma'am. Now request our officer in charge madam, Dr. Punshila Hajra Bhattacharya, to please deliver the welcome note to the esteemed guests.
Good afternoon, everybody. The Department of Physics, Bethune College, in collaboration with UGC-DAE-CSR-Kolkata Centre, has organized this one-day seminar on from heavens to title of the seminar is From Heavens to Alternate Energy on Earth, the Nucleus very simply under the UGC Star College scheme. We are extremely honored to have with us as speaker Professor Umesh Garg, Professor of Physics, University of Notre Dame, USA. Thank you, sir, for being with us here today. A very warm welcome to you on behalf of all of us at Bethune College. I also welcome Dr. Sanjeev Kubre from the Designation Center and Dr. Rajashri Rao. And thank you very much for coming with sir and in fact helping us to organize this program at such a short notice. Thank you so much. I congratulate the Department of Physics for organizing this seminar with such an illustrious speaker and that is so hurriedly, everything was done so quickly. I welcome all students, our teachers present here, and I hope this and I'm sure this seminar is going to be a huge success. Thank you, everyone.
Thank you, ma'am. I will now request our teacher, Dr. Saurav Ganguly. He will speak a few words about today's speaker, Professor Umesh. Please, Saurav sir.
Good afternoon, all. It's a great honor to have Professor Umesh with us. I'm just giving you a brief introduction of Professor Umesh. Umesh, a professor of physics at the University of Notre, graduated from BITS Pilani and obtained a PhD degree in experimental nuclear physics from the State University of New York at Stony Brook. After postdoctoral work at the Cyclotron Institute, Texas A&M University, he joined the Notre Dame faculty and has been there since. He has held guest professorship at the Free University Amsterdam, the Netherlands, BRC Mumbai, GSI Germany, TIFR Mumbai, Riken Japan, Peking University, Beijing, Jiatong University, Jiang, and BITS Pilani. He is a fellow of American Physical Society and the American Association for the Advancement of Science. The current focus of his research work is low energy nuclear structure with special emphasis on connection of nuclear physics to the physics of neutron stars. He is currently in India as a Fulbright Nehru Distinguished Scholar associated with the UGC-DAE Consortium for Scientific Research, Kolkata. So on behalf of department, I welcome Professor Umesh. So can you make এটাকে একটু বন্ধ করে দেবেন ইন্টারনেটের বন্ধ there was actually the changing is not done. So that's why they are asking. So I think just turning them off. Yes, so many. It's okay. I think it will remember. Yes.
Hello, everybody. Good to see you all. Thank you for inviting me here and for you to coming over. It's lunchtime, it's before exams. Oh, you have every excuse not to be here, but you are here, so I'm on. And I want to tell you before I start that please feel free to interrupt me anytime and ask me questions. I want it to be a conversation, not necessarily. I don't have much wisdom to impart, so if we converse, maybe we'll learn from each other. Quick question. What class are you all in? First year, second year, third year? Everybody from third year? Third year. Everybody? First year onwards. So let's see if we can talk at the level where everybody might be able to follow. But again, there's no place where I have to reach. So stop me anywhere and we'll go. Got the deal? Okay, so let's start. We'll talk about from heavens to earth, little nucleus reigns supreme. We see nucleus comes into picture everywhere. We'll tell you the story of how nuclear physics comes into being, not only what we do on earth, but what happens up in the sky. So From time immemorial, man has wondered what's up there. So maybe tens of thousands of years ago, 100,000 years ago, when we looked up, one always wondered what there is. And one tried to find answers. There were many answers, but oh, God has put a big sheet around us, and these are little rules there, which the God watches us. So whatever the thing was. And we were thinking about it, about what is the universe made? And this is a question that people have tried to answer over the years. I give you an example of something called the creation hymn of Rigveda. Rigveda, at least 7,000 years ago, maybe 10,000 years ago. There's a very well-known hymn. You guys all good. So just go and put creation hymn and read it. It's a very interesting speculation or musings about what the universe is about and how it came into being. It always talks about, among other things, in the beginning there was neither existence nor non-existence, no realm, no sky, no air, no earth. There was no mortality nor immortality, neither form nor name, neither day nor night. It was all darkness and nothing darkness. It's true, that's how the world started. How was it formed? How was the world formed? Or was it formed at all? Only God knows. But maybe he knows, maybe he doesn't know. And that is the process of scientific discovery. Ask questions, talk about possible answers, and maybe you come to an answer, maybe you don't. If you don't, you say you don't. But they were beyond that. They say maybe he does. So there's a long story as to how you would learn about the universe. So, what is the universe made? Of course, the only way to find out is by directly confronting nature by experiments. So you look at the thing, come up with some ideas, do some experiments to prove or disprove those ideas, and accordingly you can keep advancing. So that's why one can reach definite conclusions. Experiments have told us that complexity often arises from simple. What we see as complex at the core of it, at the bottom of it, is something very, very simple. For example, you have all seen the periodic table of elements. All the elements we can put together in a few columns and a few rows, and we see that knowing one column, you know the properties of every one. Knowing one row, you know how the properties are changed. So all that we put together in one. Similarly, when you come to structure of nuclei, we learn by very simple ideas. The fundamental constituents are small particles. Nature is building a simple universe. Nothing very complicated may come out. Also, the diverse phenomena can be manifestation of the same underlying process. So the apple which fell on Mr. Newton's head, the phenomena is exactly the same by which the moon is going around. Now think about this. If Mr. Newton had chosen to sit under a neem tree, and all be free of the gravitational law, he wouldn't worry about it. It would be going around. He wouldn't come to that. But it's this, you realize there's exactly the same physics which governs the falling of the apple and the orbit of the moon around Earth. Similarly, you have simple. Third thing you have to realize that intuitively what you think may or may not be always correct. The whole idea of quantum mechanics, our world is quantum mechanics. Things that we don't see, but you see the manifestation. You do not see electromagnetic waves that are powering our cell phones. You do not see the quantum behavior which is allowing us to communicate one point to another. So all that, many quite counterintuitive as you learn more about mechanics. It is quite counterintuitive, but it is real because how do we know that? Because we can do experiments and test the ideas. So that's the way we try to find out about nature. So I talked about periodic table. This was the periodic table many years ago. The Greeks had 4 elements in periodic table: air, fire, earth, and water. We were a step ahead. What did we have? The word of Panchtat. We had 5 elements. What we added to Vayu, Agni, water, Jal, and Bhumi, we added Vyod, space. Not sky, but space. So it says Akash here, but we are talking of space. More than space, the vacuum, the shoes, the Vyod. The idea that there is nothing, and from that nothing that we learn, we created the entire universe. So this, when we talk about zero, it's shunya. Shunya doesn't mean the number 0. Shunya means nothingness. Number 0 is just a manifestation of that in count. So that was our contribution to initially the periodic table. Then Mr. Mendeleev came up with what we could know the modern periodic table, which you are familiar with. Now, how many elements do we know now? 118. Everybody seems to know other things. What is the 118th element? Does anybody know? 117. 1. Hydrogen. 10. Neon. Beautiful. Okay. So 118 is called organism, named after the name is organism. But it's called all other elements. Most of the elements are known as ions. So you have, what do we go here? You have lutetium, seaborgium, borium, osmium, magnesium, tungstadium, organium, coppernicum, niobium, flavorium, moscovium. But we have organism. Why do you think is that? Why is not organism? Because there's so many ions, magnesium, etc. But this is not. Because it falls, which you don't see it here, it's the last, it's the noble gases. How do we have? What do noble gases are called? Neon, argon, krypton, next one has to be on. The same way, number 17 is called tennessine. Why? Iodine, acid. So that is the way we have the whole. Now, as I said, all you have is all these elements will have more or less similar properties. This way, you would see some development of properties, but it's very simple. So all these we could put through it, not 5, but we put 108 elements in very nice. So that is what you can see, that very simple structures work. So if you look at matter is nothing but various combinations of a few fundamental particles. The few fundamental particles, there are 6 quarks. You have heard of quarks? Have you met a quark? That's how they look like. And I can claim that because you'll never see them. They will look like this. So there are 6 quarks. And associated with 6 quarks, there are 6 leptons. So if you have quarks up, down, charmed, strange, top and bottom, the leptons are electron, muon, and tau, and for each of them there is associated with So 6 quarks, 6 leptons. If you want to be more sophisticated, you could say 6 of them, 12 and 12 antiparticles. But the rest of everything is formed by combination. I am nothing but combination of trillions quarks and leptons. Really start cutting me up, at the end you'll end up with a few up quarks, a few down quarks, etc. Okay. So when you 3 quarks make either a proton or an electron or any variant. 3 quarks are a variant. A proton is nothing but, remember that quark looks like this fellow, 2 up quarks, 1 down quark. The neutron is 2 down quarks. You bring them together, and then you bring an electron. The electron is going around. What do we have now? We have an atom. You bring a few atoms together. What do you have? A molecule. You bring some molecules together. What do we have? We have a gas or a solid. And but you know, I'm standing in front of you. Nothing but started from these atoms. So if I multiply this by billions, billions, and billions of times, the whole universe. So in the beginning, when the Big Bang happened, at some point we just created quarks and gluons and atoms. Later we formed the nucleons, and initially all you saw were atoms. So if you have protons, you can put 1, 2, 3, 4 protons together. You first form a neutron. You can form helium-3, which is an isotope of helium gas, and eventually you form an alpha particle. So 4 protons give rise to an alpha particle. So in a Big Bang, first you form protons. You bring protons together. Now, protons don't like to come together. Why do you think is that? There's a gentleman named Mr. Coulomb who says, "Thou shalt not come together." So they cannot come together. So to bring them together, either it could be a completely random process, or you have to bring some energy. That energy comes from, say, high temperatures. And that kind of high temperature we don't find on Earth or any planets, but we find in the core of the stars. That's the difference between a Jupiter, which is a big star, and Sun. Not necessarily the mass, because at the core of the Sun, you can have nuclear reactions taking place, which produce the energy. And that energy, the Sun gives. Jupiter cannot produce its own energy. It has to depend on the energy that it gets from Jupiter. So this kind of process is possible with together. So you have something like this. That's what we're talking about. These are protons. Blue protons are always blue colored by the way. Now you let them see they're going, and randomly few of them will come together, or by design, whatever, they come together. And something happens. 2 protons make a neutron. You have 2 neutrons, that's a helium-3, and then you bring 3 helium, 2 helium-3s, and you are left with. So now we have 2 protons and 2 neutrons. That's an alpha particle of helium. Now I have alpha particles. I'm making more and more alpha particles. And I have some alpha particles also don't like to come together. But if I have sufficient energy, they come together. So if I put 2 heliums together, what do I get? Chemistry. 2 protons, 2 neutrons. Now I have 4 protons, 4 neutrons. What do I have? Beryllium. Beryllium-8. Now beryllium-8 does not exist in nature. It immediately decays. So you cannot, even when you bring the 2 alpha particles together, they don't hang around too long. Immediately they separate. How do we have all the elements? That's how The two alpha particles don't work together, but three of them you bring together, they like to be together. And that makes what? Carbon. Carbon. Whole life that we know is based on carbon. Because this work of nature, the two alphas would not join, but three alphas will join together to get carbon. Now we put another alpha, get oxygen. Put another alpha, get neon. Put another alpha, you get magnesium. Put two carbons together, you get magnesium. You put a carbon and oxygen together, you get silicon. You can also get silicon by putting alpha or magnesium. And you can keep going up. Put two silicons together, what do you get? Absolutely no idea. You get iron 56. Okay. And as we learn at that point, things go crazy. So if we look at the Big Bang, in this picture, what you see is, what did we see as a function of mass? So this is mass 1, this is 2, this is 3. At the very beginning, it was mostly mass 1. This is the hydrogen. There's a little bit of helium and even more little of lithium. Think about it. This is a factor of 10 raised to power 10. 10 billion times. Lesser helium and even 10 times less or 100 times less. That's all was formed at the Big Bang. You have heard of the Big Bang? Out of nowhere, suddenly, Big Bang happened. Things out of nothing. Some energy was created, that expanded, and cooled things down, and so things particles were formed. And we know that it happened because we can see the remnants of the Big Bang. Even now, the universe has an ambient temperature of 2.7 degrees Celsius. And that measurement of that temperature became a direct link to the theory. The Big Bang predicted that was just expanding, it's getting cooler and cooler. So at this time, up 13.7 billion years after, it would have a temperature of 3 degrees, and that's what we see. Okay. Now, in early stars, when we look at early stars, we find elements which go up to about mass 3. Okay. But today's stars, we see what we find up to mass more than 200. What's the highest element that we find on Earth? A bit louder. Lead. Lead is okay. Lead is have you heard of thorium? Uranium. So up to uranium, we actually find uranium is not stable, but it is has a lifetime of 5 billion years, so 6 billion. So it is like stable, but nothing beyond very great. So 92 to 118, that long 26 elements that you saw, they were all created by man. But up to uranium we find. Now I'll tell you that that is a mystery as to how we form elements which are very high. All the gold that we are wearing, even the silver that I am wearing, cannot have been formed this. And that has to do with how the nuclei are. So this is just a picture. It says the net energy of the nucleus. Okay. Now, and this as a function of mass. Now, you know, any system wants to be in the lowest state of energy. Okay. So, you are here, you want to combine neutron to alpha, etc., and you reach here. Yeah, that's where you reach minimum. That's around iron. But after that, you need to put energy to create. Okay? You cannot add things because as soon as you add, what's to go back. But we see up to uranium-238. How did we go from here? The same way I started talking about alpha particles, bring alpha particles, we carbon, we bring two carbons, we bring magnesium, we make silicon, we bring two silicons, we bring 14 alpha particles together, we make iron 56. And that's where the process comes to a stop. I cannot add another alpha particle to iron 56 and make nickel 6 because it would immediately come back. So how did we form? That is the story we will eventually try to go through. Okay? But before, because we are talking of alternate energy, so let's see. If you are here, you would like to come here and in the process gain energy. What do we call it? We call it fission, breaking. If you are here, you would like to come here and we call it fusion. And also see that this energy drop is very fast. So that means the amount of energy I gain in fusion is much more than the energy I gain in fission. But you can have fission in nuclei and in the process gain energy. Okay? So if I have 25 atom in my pocket with me, I reach into my pocket, pull out a neutron, I keep a supply of neutron in my pocket. Pull out the neutron, attach it, what happens? Takes uranium-236, which immediately fissions into an atom of barium and an atom of atom nucleus of barium and krypton, and it gives me also 2 neutrons and 179.4 MeV. One thing is that we realize that I only have to spend 1 neutron by far. Because the process gives me 2 neutrons, then it will give me 4. Compound interest happens. So like a good banya, I invest 1 neutron and would add in this. Okay. But I also gain 179.4 MeV. How many of you are familiar with this unit? Everybody, nobody? The first year students have never heard of it? Okay. Have you heard of joules? Okay. So this is nothing. 1 MeV is 10 raised to negative 13. Now think about it. 180 MeV. 10 raised to minus. That gives you 10 raised to negative 11. That's not much for energy, is it? How much is 10 raised to negative 13 joules? Think about this way. What is joules per second? It would be 1/100th of a nanowatt. But we still get a lot of energy. Why do you think it's that way? Another number comes into picture that you know as. You know this number? Avogadro's number. Avogadro number 235 gram of uranium. Just a 1/4 kilogram of uranium has so many atoms. That means 1 gram of uranium can give you 10 raised to 11 joules. 1 gram, 10 raised to 11 joules. How much is that? I think I can give you a homework to calculate. How many lamps do I have here? 1, 2, 3, 4. Okay. You know how much is what is these lamps? About 40 watts. 40 watts. So let's make 5 of them. Life is easy, calculation is easy. 200 watts. Okay? Think about it. For how long I add the fans here? Make it 500 watts. For how long can I keep these lights on before I consume 1 gram of uranium? Will you take it as a homework? I might come back on Monday and ask, or I'll ask the professors to check. Figure it out. It's a lot of energy. How much? It's equivalent to about 20,000 kilowatt hours. You know what kilowatt hours is? The unit household. How much free energy does Mr. Kejriwal give his people? 200 kilowatt. How long can he come? He gives 200 per month. 100 times. So we can give more than 8 years of free power. I can tell him, keep your power, I have my 1 gram of uranium in my pocket. So that's typical of typical household. 2 years. That is the power. Small amount of uranium can give huge amount. And process you have seen, you have uranium and neutron comes, 2 neutrons come out, you have another uranium, the process goes on. And you don't stop, what happens? Boom. We call it an atom bomb, which is a lot of energy released in 1 instant. You have heard of the Hiroshima bomb? Do you know how powerful was that bomb? Next time before I come give a talk, I should give them homework questions. A pre-work question. It was 15 kilotons. 15 kilotons TNT. What is that? TNT, just so many TNTs of explosion. A typical bomb that our military uses is 500. So 2 of them make a ton. If I had 15 kiloton, that's 30,000 of those bombs put together at one time. Boom. No wonder it has so much destruction. Our standard planes, Rafale, will take maybe 4 of these bombs. Our biggest bombers might take 20 of them. 30,000. So that is the kind of power in their programs. But if you can somehow control this process where it doesn't go crazy, then what do you have? You have a nuclear reactor. So nuclear reactor is nothing but a controlled nuclear bomb. Okay? So what you have is in a nuclear reactor, you have fuel rods, these are the fuel rods, and you have control rods. Control rods are made of an element called cadmium. Cadmium, what's the atomic number of cadmium? Anybody? 46. So cadmium likes to eat neutrons for breakfast, lunch, and dinner. Really likes to. So it absorbs neutrons. So if I have these rods, they are eating most of those neutrons. So what we do is we take these rods out from them. I take the rod out, the reaction increases. When it goes beyond a certain limit, I bring the rod in, then it comes something. So that's what a nuclear reactor. And then all the energy that goes to heating the water, which produces steam, which runs the turbine, and we have electricity. So a nuclear reactor basically, of course, because there's lots of radioactivity, etc., we have a containment structure, we have to have very no connection between outside and inside, so that no radioactivity can escape. There are many practical issues, but ultimately this is what is good. You know how much a nuclear power plant, what kind of power can it give? Most of our reactors are 250 megawatts. Now they are designing and building 100 1,000 megawatts, a gigawatt. Of course, we also make a gigawatt thermal reactors. We have in India. But a gigawatt thermal reactor requires, I think, 50 wagons of coal every day. Think about how much coal, how much it is producing. It produces tons of ash. We don't know what to do. Whereas here we need few kilograms. It's a wonderful idea. Alternate energy. Okay, so far so good. Now we come to the other side. That was fission. Now we can have fusion. You have already seen the one basic reaction. 4 protons coming out with helium. So this is 4 protons. It's a helium, 2 positrons and 2 neutrinos. And it gives out 25 MeV. What was the for the fission? 180. This is 25. Why do I think that's much more? It's 7 times less. I made a statement that you can get much more energy from fusion. Any idea? Where is the contradiction? Yes, louder. Go ahead. You are probably correct. It's only 4 grams if you want to call it. 4 particles give you 24. How many were there giving you? 235 of them gave me 175. That is less than 1. Here, 6 times. So it is more than 6 times more powerful energy. Much, much efficient. Okay. It's so much energy. Sun, our sun gives out 10 raised to 26 watts. That's a lot. That's what keeps us warm. Even in winter, keeps us warm. And it has been giving that for 5 billion years. It keep giving it for another 4 billion years. The first time we realized that that's where the sun or stars get energy is from nuclear reaction is because there's no other way we can figure out that so much of energy would be given for such a long time. If we had thought of thermal processes, sun would have disappeared less than a billion. We would have consumed that last. Only about less than 100 years ago, this idea came along that at the core of the stars are the fusion reactions. So now you have lots of fusion. I said there's neutrinos here. Do you guys know what neutrino is? Yes, no, maybe? Neutrinos are stable fundamental particles, but they are also the most abundant particles. But they have no charge. That means they have no electromagnetic interaction. They have almost no mass. They have almost no gravitation. In fact, they interact so weakly with matter. They are very inertial. So, through my thumb, 100 billion neutrinos are passing every second. They don't want to stop and say hello. A human body may capture a neutrino once in 70 years. I'm approximately waiting for one to come and be captured. So we have neutrinos, but they don't interact. But we can see them coming from inside. Even with minimal interaction, we can't figure out. Because we put huge detectors which are tons, and then we see in a year. That is, again, that we know that because they interact very weakly with matter, even though they are formed in the core of the sun, they can still get out. And so the light that is produced in the core of the sun, if there's any, you cannot see it because we get absorbed with the rest of it. The light we see is from the sun. Neutrinos are coming from the core of the sun, from those nuclear reactions. And that's how this is a neutrino picture of the sun. So if I use a neutrino detector and point towards sun, that's how I see the this is the outer part of the sun. So we know how neutrinos are found. Now there's a whole branch of physics or astronomy which is called neutrino experiment. We look at neutrinos coming out that we can learn a lot more about the stars. Okay, so we talked about fusion, lots of energy. And of course, we have managed to do something useful. We have made bigger bombs. They are called the hydrogen bomb. Okay, remember the atom bomb, how much was it? 15 kiloton. Hydrogen bomb is megaton, million ton. 60 times more. Think about it. 20 lakhs of these bombs up together. Thankfully, we have used in the gas tank. The biggest bomb mankind has made was 50 megaton. 10 crore bombs. Fusion. The power is so much we haven't yet figured out way to control. So fusion energy is still about 20 to 30 years away. It has been about 20 to 30 years away since I was a child. It's always 20 to 30 years away. But hopefully in the next 20 to 30 years, we will have something like the working, or at least the prototype fusion. So that's where, and if of course we have that, many of our energy problems are solved. Why? There's hydrogen everywhere. Oceans are full of water. We don't have to dig uranium out and do all kinds. Sure, please.
Some years back, we have had a term like cold fusion. Yes.
He's talking about cold fusion. When you have to fuse, you have to bring huge amount of energy. So a hydrogen bomb, to make a hydrogen bomb, you first have to explode an atom bomb, which provides the energy to fuse the area and material, and that makes the hydrogen. So about 30 years ago, an idea came along that under certain circumstances, we did not need as much energy and we could have what is known as cold. So you brought atomic spray neutrons, etc., and you saw neutrons coming. That was given as a sign. The neutrons only come out nuclear reactions. So there was cold fusion taking place. And if it was really happening, life would be significant. That was solved. The solution about was. But that eventually fizzled out. We discovered that effect was being described many different ways. So there was one case that I actually was not down at that time. We heard this buzz about how they have observed cold fusion. Let's measure it. At 5 o'clock, everybody goes home. This one guy, students stay there, and 5 o'clock, there's no more cold fusion. Whole light is struggling and we cannot see it. Next morning, the professor comes, he said, I did say, we'll start seeing it again. The professor probably, like most professor, will do that. It doesn't happen. And at 5 o'clock, 5:30, it disappears again. This time, the professor is present. And they are struggling. Yeah. Turned out about 100 meters away, there was a cyclotron working. which produced these neutrons. So they were not seeing neutrons from cold fusion, they were seeing neutrons from when the cyclotron operated 8 to 5. So the medical cyclotron, it started about 8 o'clock and shut off. As soon as they realized that cold fusion ideas, it's a mini cycle. So that was the goal. So fusion requires tremendous amount of energy, but it also gives tremendous amount of energy. The temperatures you are talking about are millions of Kelvin. Now, we don't know anything which would not melt. How do I pre-contain? So there are ideas basically you create a plasma and use magnetic fields, keep it there. And then the question, first thing is, can you keep it like that? Secondly, after you succeed to keep it, how do I get energy out? So there are various ideas, get it out in the form of electromagnetic radiation or that kind of which will oscillate this plasma and electromagnetic wave and that gives you many things. But it is still, what did I say? 20 to 30 years away. And hopefully, we will not be giving this lecture at my age and say 20 to 30 years. Okay. How are we doing with time? Okay. So we talked about you form carbon, carbon from oxygen, oxygen neon, neon from magnesium, etc. etc. So in a star, what happens if you look at the core of the star? It looks like a honey. At the very inside, you have where's the hottest, you have silicon fusion, and etc. etc. But do you realize once it starts making silicon, silicon is fusing, it's making iron. At that time, it has to come to a stop because it cannot make anything else. That's when the star starts dying, unfortunately. So, if you look at our sun, has been giving for about 4.5 billion years. You keep giving for another 4 billion years, then we start expanding them. You get a little bit cooler, a warmer, and that becomes what is known as a red giant. It would be much bigger, cooler. Red means will be different temperature. It would be to come to the orbit of Mercury, it follow Mercury. You could almost touch the sun with that. But of course, it will be so cold that we probably won't be around, not in this form. So, of course, my American friends say, we'll be all dead. I tell them, we'll be dead. I'll be around. I mean, I keep going. So I'll be in some form or other. My Atma will be around to watch the sun. But that's where the sun goes. Eventually, it will explode to a nova and finally it will become a white dwarf. A white dwarf is a retired anyway. Nothing better to do, not worth anything, but doesn't have much life in it. Just waits to die. But it doesn't die because it has nothing. What will happen that it might accumulate more material and then become a regular star again, or more likely it will be gobbled up by another star. So that's where our sun is, in about 14, 15 billion years. If you have a massive star, big star, 25 times the massive star, then in our sun, by the way, we don't see any reactions beyond hydrogen. Because the mass is not enough to create the high temperatures that we do. But if you have a massive star, it could be doing hydrogen burning for maybe millions of years. Helium burning could be going for 1 million years, 500,000 years. Carbon burning, 600 years. Do you see this pattern? Oxygen burning happens for about 6 months. The silicon burning, etc., happens. Notice that it took a long time to get going, but once it got going, it's ready to die. So a star may take millions of years to form, millions form. and then it works, etc. But when the time comes, dies very fast, very quick. So if you think of a small star, it becomes a red giant, a nebula, and a white. Okay? It's a large star, it becomes what is known as red supergiant. Then you have a supernova explosion. And that supernova explosion may lead to a neutron star or a black hole, depending on the mass. Have you heard of the term neutron star? Neutron star is a sun concentrated in a radius of 10 kilometers. Another homework. What would be the density of the mass of the sun over a 10-kilometer radius? That is calculated. The answer is 10 raised to power 17. Right. And that's it. But I was telling you the death of a star. So this is a star, nicely shining as we do it. That's not right. I have to show you something else. If I can get this more. That's how long it takes for the star to die. Less than a second. Collapses on itself. So what is happening in a star? The gravity wants to collapse. Gravity always points. The spherical object, gravity is pointing towards center. So gravity is collapsing. The nuclear reactions that have been happening are keeping it gravity at bay, like Govardhan. But at some point you remove that. Because what happened? After time, it cannot do anything. So there's no more nuclear reaction. So it keeps, that's what you saw, collapse. And then at some point it explodes. And that's the supernova and gives out all kinds of things. This is what is left of star. You want to go back? Look at the time that we are talking about. It is realistic time. When we talk about Kshanbhangu, this is even less than Kshanbhangu, just comes. And that's what gives rise to a supernova that's all spreads all over the universe. And this is an image of an aftermath. This is Cassiopeia. So this is what a star looks like. Nothing particular. There are so many stars, and but later you see this image. A supernova gives so much energy that the star can burn very, very bright, brighter than 1,000 suns. Remember that term before? Brighter than 1,000 suns. Srimad Bhagavad Gita, Lord Krishna says, I am death become brighter than 1,000 suns. And the reason it became famous that Oppenheimer was the creator of the first atom bomb. When they tested the bomb and when he saw this light, that's what came to his mind. I am death become brighter than 1,000 suns. He knew about that. So that's what it is. So suddenly you have a very, very bright star. The supernova happens somewhere close by. We will see a very bright star for months or years at a time. It's so much. There have been some supernovas that people have recorded. The earliest recorded one was in year 1060. The Chinese recorded. There was a bright star which lasted a year or something, and then more. I'm sure people have seen them, they didn't record. Have you? Oh, maybe I should not be mixing. Anybody, any question? Anybody with a question? Have you heard of Star of Bethlehem? Have you heard that when Jesus was born, there was a bright star And these three wise men followed that bright star and brought gifts to Jesus. The three magi, they brought gifts of incense, myrrh, and gold. They came from the east. So the speculation is that that bright star was nothing but a supernova explosion near, which happened to be visible there. And these guys could have come from as far away as India, because Indians were very much at first started. So they saw this new thing and they were asked to find out what was happening. And they went all over. These are all speculations. I have no idea if Jesus actually existed or it was a developed star. But that's the story. So the story that may have existed. One of my colleagues gives this lecture every Christmas about the star that comes. So that would be a supernova because it was a new bright star which appeared. And it was true that whenever anybody saw a star like that, they always thought that something major was about to happen. Because it's an unusual. We used to think the same way for eclipse. Solar eclipse, etc. Now we know it's a deep thing. So you don't need to do all the dramatic that we do at the eclipse. We started doing it because we did not know what this, so we thought of it as omen for something. So this is what a supernova is. So for a supernova, now we started with the story. How do you form elements? Iron, iron. You cannot form. There is something we believe now, something called R process, rapid neutron capture. I have nickel, I have iron 56. I bring my one neutron attached to it. It takes iron 57. It's immediately decays with cobalt. But before it decays, I add another one, and I have made 58. That makes nickel 58. And if I can keep doing this, before it decays, I add one more neutron. The process keeps going on. I can make heavier elements by the process of adding neutrons. This is called ion. The probability of this process is very, 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 very low. But if I have lots of neutrons, something will happen. Okay? So if I have an ion, I go to Flipkart, order 5 tons of neutrons. I might be able to do something, but that's not it. So if we have it, but first the idea. So this picture simply shows that this is where we are, the stable. These are all the stable nuclei that one sees on Earth. I told you, you could not form anything beyond. Where did they all come? If you follow some ideas about our process, something like that can happen. I want you to see this picture as the elements are formed and look at the time scale. This is T equal to 10 raised to negative 4, 0 time. Okay? How quickly you were able to form up to here, and then they decay down stable. We are still talking of 1-2 seconds. So if I have sufficient number of many more than a few tons, then I would be able to. This is the theory. But the experiment is, yes, we see all this code around, we see the decay. How do we connect them? And where do we find these neutrons? One source of these neutrons are the supernovas. Coming from the experiment. Or the physics, or action with reaction, there are huge number of neutrons coming. Those neutrons with other elements can form something more. Okay. Now this material goes and falls on other places. That star, when it explodes, it already has some heavier. So those neutrons add more heavy. And in this process, if you keep going on, you eventually will reach a stage where you start seeing. So that is what it is. This is the same process. This is real time. You see that how long that takes. That's about it. And you can see which masses are formed and eventually you form up to mass 3. Okay. That previous one was slow process. This is the real time. So it takes a second. Taking the average. So we are made of star stuff. Each heavy element in our body was built and processed through 40 supernova explosions in the beginning. I told you first supernova explosion went from say iron, titanium, into gadolinium, gadolinium, etc. So 40, all the gold you ladies and gentlemen are wearing. Just remember, 40 stars have given their lives so that you could be glittering. So that is one source where we find the neutrons and we can make everything. There's another source now we have discovered, which may be even better. So if you look at, you may or may not have seen this picture. This was a few years ago. These are 2 neutron stars came out of supernova, and these neutron stars happen to come very close to each other. They come and they collapse into each other. They give out these gravitational waves, which you can see, and they also give out electromagnetic waves. In these electromagnetic waves, we can see signs of the elements. Because each element of chemistry, you know, has very specific radiation that comes from each element. So I can look at sodium, you see that yellow line. Neon, you see that red line everywhere. As soon as you see red color, you know there's a neon. You see yellow color, you see there's a sodium in there. So there are various things. So we can analyze the light coming from this thing, which we were able to observe. And we actually saw as many heavy elements form in this star mission. Up to at least gold. So now we know where all the gold came. Came from far away somewhere, 2 neutron stars collided and created gold stars. Or some supernova explosion series over the thing has created gold stars. So I think that may be good time to stop. I will not go through fusion. So thank you very much for your time. And I'm up for questions, but before, because still I want to show, my advisor had told me that when I give talk to non-experts, I should not use any jargon. I hope you did not find too much jargon in my talk. Was it accessible to most of you?
Yes, sir.
And I hope I'm not supposed to overwhelm you with detail. I didn't give you. And he also said I should use some animal pictures to keep your attention, which I did. So here's the animal. This is also called the question figure. That means you are welcome to ask questions, but if you ask nasty questions, I'm not responsible. Now, thank you very much. Any questions about anything I have said or did not say? We can talk about politics, we can talk about movies, anything, or fiction. Whether trying to ask a question or just helping each other. No questions, nothing. Either I did a very good job or I did a lousy job. Yes, ma'am. The same talk I had given about 25 years ago, or 20 years ago. How does that neutrinos have no mass? Okay. But now we know they have some very little, very little. Think of it. An electron has a mass in terms of energy, 511 kilojoules. That corresponds to 10 raised to minus 32 kilograms. A neutrino may have a mass of an electron. So it's 500,000 times smaller than electron. So it has almost no mass. Your question is, there's no mass, no charge. How does it return? So we know of four forces, four different forces: strong, weak, gravitational, electromagnetic. So we have decided it cannot be electromagnetic. We have decided it can't be much of a gravity. If we are talking of 10 raised to minus 26 kilograms. Okay. So strong happens only between nuclear particles. The only thing it interacts with is the weak. And the weak force is called weak because it's weak. So it's very, very weak. So that's what it makes it very weak. Interact. But it has a spin, has a certain way it goes on, something called illicit. And those are the things that can be captured by weak interaction. Or it's produced in weak interaction programs. So it can capture. There was an experiment where they first observed where they use chlorine, literally washing liquid. Okay? And a cool type of it. And they let the neutrinos come. And chlorine by capturing a neutron, it can become argon. And a neutrino, it can become argon. And we can every year we redo it and see how much argon we can find. So we find so many argon here. That way we can see how many neutrinos were come. So that's how we have huge detector. There was a detector in Canada where they put, I think, tons of heavy water. And then a few years you saw. So it is, yes, it does interact. Right. Anything else? Any other question about this biscuit? We can discuss the quality of the biscuit. Anything else?
Sir, one more time. One more time.
No, I still have this. The B is something. I think it's against laws of God to say no. So